right, good morning and very welcome to my talk. My name is Zilin and my talk is about a Hoare Logic style formalization of refinement types. What I do in this work is that I formalize a small core calculus with refinement types in Agda, and this formalization uses a Hoare Logic style encoding. Let's get into it. What are refinement types? In this work, I use the term refinement types to mean subset types. Imagine that we want to define this positive natural number type. This type is divided into two parts. One is the base type, a net, and another one is a refinement predicate, which tells us how we want to refine this type. It says that the value of all the inhabitants of this type has to be greater than 0. What is good about this type? When we use this type in the function definition of a division function, we can know by type checking that the divisor is never 0. So division by 0 exception can never happen. Refinement types are very expressive because we can define new subsets of existing types. So as developers, we can say very precisely about the properties that we want the inhabitants of a type to hold. At the same time, refinement types are very easy to use. Their syntax is intuitive. Users just annotate their types with the logical formulas. In languages equipped with refinement types, usually the design principle is that we want the type checking procedure of the language to be decidable. What it entails is that in program verification, if we use such a language, what we get is fully automatic verification, and no user intervention is needed. And this is why refinement types are very popular. Technically, sitting at the core of a refinement type system is the subtyping. Traditionally, subtyping can be defined using these two rules. The subrule says if one type is a subtype of another type, then they must have the same base type B. And the refinement predicate in the smaller type implies that of the larger type. Usually, we need to have a separate subfun rule to handle functions because of the control variance in the argument position. The logical entailment in the subrule is usually outsourced to an SMT solver, and this is why the logic in the refinement predicate has to be chosen very carefully so that SMT solving remain decidable. Refinement type induced dependencies. Let's look at this simple let expression. When we type this expression, we start from the constant 2, and the type we give it is a type which is exact, saying the value has to be equal to 2. As we move on to x plus 1, we extend the context with x. And the inferred type, mu equals x plus 1, this type depends on the value of x, which is the variable in the context. Coming to x less than y, the context is further extended with y, whose type, nu equals x plus 1, depends on a variable in an earlier entry of the typing context, which is x. We can see that in the typing judgment for refinement types, there are two types of dependencies. One is between the inferred type and the context, and another one is among the entries in the typing context. And that forms a telescopic context, which means types in later entries of the context can depend on values in earlier entries of the same context. And this is why the typing context has to maintain a particular order so that the dependency doesn't fall apart. The connection between Hoare logic and refinement types has long been recognized. And let's see how it's done. This is a Hoare triple, with P and Q being the pre and post conditions of executing S, which is the program. There are many languages that are verification oriented, which allows users to annotate their program with assertions. If we represent this Hoare triple in such a language, we can roughly write it as the following. For a function from type B1 to B2 requires P ensures Q. What it means is that the argument has to satisfy the assertion P, and the result of this function needs to satisfy the assertion Q. We can easily rewrite this annotation using refinement types like this. So the P and Q become the refinement predicate of the input and the output type of this function, respectively. So here we established a connection between Hoare triple and refinement types. We can extend this correspondence a little bit further. Let's formulate a Hoare triple slightly differently and be more explicit about the evaluation result of S. We make the postcondition lambda mu q not only describing the program state after executing S, but also it is a predicate over the value of S. Again, this is the typing judgment for refinement types. And if we expand the syntax of tau I in the context and tau, we get this judgment. Let's lift out all the base type from the refinement type, both in the context and also in the resulting type. And we ended up with this shape. We can observe that the pink part of this rule, this judgment, is actually the typing judgment for a simply typed language. And this judgment is augmented with two propositions. One is on the context, and one is the result of evaluating E. This mimics the structure of a Hoare triple. The judgment in the box is what my formalization is based off. We split refinement types into two portions. One is the simply typed portion, and another one is about the refinement, which is encoded as a Hoare triple. Traditionally, if we want to encode a refinement type in a dependently typed language, the most obvious way to do it is to encode it as a sigma type. It, however, introduces some difficulties in the encoding, and some more advanced techniques are needed. For example, induction recursion, which makes the formalization difficult to work with. The benefit of this Hoare style formulation is that it eliminates dependencies between types and terms, and it doesn't require the telescopic typing context. So the formalization is much easier to work with. Also, what we get from Hoare Logic is its backwards reasoning mechanism, which is the weakest precondition predicate transformer. What it tells us is that we can get a very straightforward type checking algorithm running backwards. Specifically, in the Agda formalisation that I present in the paper, I study a very small language, which is a lambda calculus with primitive types, products, and it is restricted to first order functions. In the Agda encoding, we index the type of the deep syntax with the typing context and the type of the of the object language. So E and F are the Agda syntax for the object language terms. And on the right-hand side, they are the types of these two terms. And we can see that the Agda types are indexed by the typing context, gamma, P, and also the inferred type, Q and R. What it achieves is that it unifies the deep syntax and also the typing rules. So when we construct the terms in the object language, we get type checking for free. And the constructed expression is type correct by construction. We give a denotational semantics to the language by interpreting terms in the object language as shadow Agda terms and types in the object language as shadowed Agda types. The refinement parts are shadowly embedded, we prove some key meta properties about the typing rules. We prove the refinement type soundness and completeness with respect to the denotational semantics. Now let's move on to the backward reasoning. When we type check a program with refinement types, we require in our setting, all the functions are annotated with types, and they are the only places where annotations are required. The type checking is split into two stages. The first stage is about the simply typed portion of the language, and the second stage deals with refinement. So imagine we have already worked out the base types. So we already know gamma and B here. In this typing judgment, if we think of it algorithmically, the inputs are E and Q, and we want to work out a P, which is the output. So the way it works is that we take the user annotated postcondition and we work all the way backwards until we reach a weakest precondition. And if the weakest precondition is implied by the user annotated precondition, then it basically means the program is well typed. How do we define WP then? In Hoare Logic, the WP definition for an assignment statement is very straightforward, just as a substitution. Since our language is a purely functional language, we can think of any expression, E, as an assignment to a fresh variable X. So for any expression in our language, we can define WP in the same way as a substitution. We prove the soundness and completeness of the WP function with respect to the typing rules. Concretely, we say if we can type E with the precondition P and postcondition Q, then P must imply the weakest precondition. Conversely, we must be able to type the expression E with the weakest precondition as the precondition and Q as the postcondition. What it does is essentially aggregating and delaying all the proof obligations that it sees along the typing tree. So we can leave the delayed proof obligations to a later stage, and they can be discharged either by an SMT solver or by users. There's one drawback with that WP definition, which is that it doesn't respect the type annotation instead of inspecting the function definitions. What we want is to use the user annotation as the function contract. How do we achieve it? There's a good example in Hoare Logic again, which is the while loop. For while loops, because of the termination problem, usually it requires a user annotated looping variant I. The way we compute the weakest precondition then is by defining a pre-function which immediately returns the user annotation when it sees a while loop, and also a VC function which generates verification conditions. It checks the validity of the user annotations. We can do WP in the same way as pre and VC. And we prove the soundness and completeness of this combination with respect to the typing rules. The forward direction says if we can type E with P and Q, then VC must be true and P implies the weakest precondition. The other direction says if we know VC is true, then we must be able to type the expression E with the weakest precondition and Q. The language that I studied in the paper is very preliminary, and I outlined several lines of future work in the paper, and here I just want to highlight two of them. One is adding more language features, like higher order functions, recursion, impurity, and concurrency. it's yet to be seen which of these language features are compatible with the Hoare Logic style formalization. Seeing that we decompose a refinement type system into a simple type system plus Hoare Logic, we're curious to see if we can use a different program logic instead, and what kind of type system it yields. My talk concludes here, and you can find all the source code online via the link or the QR code. Thank you, and I'm happy to take questions.